Hi, I'm Nikolay. I'm CEO and co-founder at Coroot, and today I'm going to talk about PostgreSQL on Kubernetes. Few words about me. I'm initially like my tech career started from being in operations, IT operations. So I am an admin guy. So before my entrepreneur journey and start building on something in observability space, I worked as the head of infra in pretty big company. So and Coroot is my second attempt to make observability simpler and easier for developers, engineers. And so now I am CEO and co-founder at Coroot. We built open source observability tool, that focused on gather everything we need to to provide users with answer what's happening in your system and what's wrong and how to fix it. So it's open source. Just check it on GitHub. And about today talk, I'm gonna talk about PostgreSQL on Kubernetes. But before, I want to highlight a few ideas about why, what does it mean to run databases in production environments, and why we may need to run them on Kubernetes. Then we will see how to run Postgres on Kubernetes, and then I prepared a few experiments. We will break things on purpose, inject some failures into our system, and see how our automation can handle all these failures. So a few words about running databases on Kubernetes on production in production. So it's pretty common to think all the possible tasks to run in running database in production. We can split into two phases. The first one is day one operation. When we need to deploy a database, we need to configure storage, replication, we need to configure access, create users for applications, administrators, and so on, and perform basic pre-launch checks. And usually it's done only once at the very beginning, but currently every big company uses infrastructure as a code approach, which allows you to automate database provisioning to be able to reproduce your environments without the need to configure everything manually. And day two operations include backups, everything related with point in time recovering, monitoring, alerting, handling disaster disaster recovery, failover. Also, our databases need to be upgraded periodically, and performance tuning and scaling. From my perspective, it's most complicated part because it requires continuous effort. It requires a lot of expertise, how to tune our databases or troubleshoot any performance issues, and how it can be solved. I've seen many approaches here. The first one is having your in-house DBAs. So usually it's dedicated guys who have strong expertise in running databases. They usually focused on one or several databases, like we might have Oracle DBA or PostgreSQL DBA and MySQL DBA, because it's pretty there can be significant differences in database design and so on. So, uh, but for smaller teams, it could be not so efficient to hire experienced DBAs because those guys usually pretty expensive. And but at the same time, you will have full control on your infrastructure. Uh, Usually, small companies and startups prefer to hire outsourced DBAs because it allows them to have pretty like highly experienced engineer for fraction of the salary of those DBAs because they work like a shared resource and but there can be challenges for even challenges for businesses who requires uh, like strong availability of their system because it can be some delays in communications, and also it can slow down development process because every question about indexes can it can take some time to reach out to external experts. And now I see the trend, which includes like uh, I would say digitalize the knowledge about how databases should run, because every cloud provider try to offer us managed services, and uh, they offer it like a replacement for DBAs. Like you don't need to know how set up replication, for example. It can be handled automatically by the system, and it promoted replacement for expert. Um, in real life, in fact, when you deal with, for example, AWS RDS for PostgreSQL, for MySQL, it, 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 it doesn't actually mean that someone manage your databases manually. They just built a software that automated all day one, day two operations for you. And if you run, for example, your database on AWS as a managed services and you face some performance issues, for example, your database needs to be scaled, or you have issue with, wrong indexes or performance resource consuming queries, you it's your responsibility to detect and fix it. Additionally, monitoring provided by those services, like pretty simple. And if you want to be able to troubleshoot database performance, you need to integrate some external tools. And also, it's always vendor lock-in because it's pretty easy to migrate from AWS PostgreSQL to some external database if the database is small. When we're talking about bigger databases, it's always a challenge. And also, you have to pay more for resources because you use some automation provided by the cloud vendor. And is it possible to have the same user experience but without vendor lock-in? Let's think about it. So we want to have the same experience and the best from both worlds. We want to use like our open source database, like PostgreSQL, MySQL, but like for example, there is no single vendor behind PostgreSQL. And it's it looks like no vendor lock-in here. But we want to run our databases anywhere, in any cloud, on-prem, and even in air-gapped environments. but we want the same experience as we have in clouds. We want to automation for day one, day two operations. And also, it should be cost effective. Let's think, is it possible or not? And I see that the Kubernetes is a game changer here because it provides us with a unified API. So our software that automates our operation don't doesn't need to know about low level, for example, bare metal servers or and so on. Kubernetes provides us with some middleware. Uh, and it provides us with API like we uh, can run container or we can scale our nodes. And also, having such APIs allows us to build operators. Operators are like piece of software that know how to run specific systems. For example, operators for databases uh, know how to run PostgreSQL in high availability mode. They know how to perform backups. They know how to restore from backups. They can automatically initiate switch over to replace unavailable primary server and so on. And to build Kubernetes simplifies building such software because we don't need, we can only operate at the higher level. For example, our code can ask Kubernetes like run a container somewhere, and Kubernetes will schedule this container to node with enough resources. It will connect volume if necessary. It can easily scale it down, up and down. It also can handle everything related to volume resizing, and also it can schedule cron jobs, for example, for backups. It can perform rolling upgrades, replacing instance by instance with a new version. And also Kubernetes provides us with leader election API that we can use for for consistency. We can be sure that, for example, and we can don't we should not think about it at the operator level. So we build high level operator that helps us run our databases. And now we have many different operators on the market. I mentioned like the most popular of them. The most popular these days is cloud native PostgreSQL, which initially be released by Enterprise DB, the biggest PostgreSQL vendor. The second one is Zalando, operator built at Zalando. Like, but I will not talk about how to choose the operator because some of them are pretty similar, but cloud native, for example, cloud native PG doesn't use Patroni as a cluster manager. But let's just go with cloud native PG in this talk. And a few words about high availability. Operators doesn't don't guarantee 100% availability because Kubernetes is pretty dynamic infrastructure. For example, nodes in your cloud can appear and disappear, especially if you use spot nodes. Something can happen with volumes, but operator guarantee that they will handle such failures and make your database available again. And as an engineer, I prefer to know how the system will behave before something bad happened. So, like the pretty close analogy here is that we can use our chaos tests as a crash test for cars, but we don't need we can do it much cheaper, and it's perfect way to see how the software will handle different failures, and we it allows us to understand algorithms, approaches, and so on. So let's see. Let's deploy some PostgreSQL cluster on Kubernetes. In my case, I will use K3s cluster. It's a simple Kubernetes compatible control plane. So my cluster has 3 nodes. I installed Cloud Native PG as operator. I configured Cloud Native PG to provision a highly available cluster for me with 1 primary instance and 2 replicas. I also implemented a simple app in Go that performs query that works um, uh, with primary and replicas at the same time. And also have a load generator. Is pretty simple app that generates that calls the app, and I use Chaos Mesh. It's also an open source Chaos orchestrator, and Coroot for observability. So here is a service map built like created by Coroot. I just installed these components, and Coroot created a service map for me. And now we can see how our environment works. We have a PG cluster of 3 instances. One of them is a primary, and 2 are replicas. The PostgreSQL cluster works with Kubernetes control plane. It uses it for leader election. Also, we have our app that generates like 600 queries per second to a Postgres. We also can see Coroot component called cluster agent. It scrapes Postgres related metrics from our instances. And also we can see how K3s agents, it's some sort of, similar stuff as the kubelet on each node that performs readiness and liveness probe. So we see all the communications because we use eBPF, and it doesn't require any instrumentation. So we see all communications in our clusters. And few words about observability here. We're going to use eBPF-based metrics for service-to-service communication instrumentation. Like we install Coroot agents on each node using daemon sets, and it uses eBPF to capture traffic and it parse application level queries. It can recognize HTTP, PostgreSQL, MySQL, and many other popular protocols. It also uses eBPF to generate some sort of traces, but in fact, it's like individual spans. So I will show it a bit later. Also, we will look at our logs, system metrics, such as CPU, memory, disk, and network-related metrics. Also, we will use Kubernetes metrics for understanding what's happening at the control plane level, the statuses of each instance. And also to understand what's happening inside PostgreSQL, we will use Postgres-specific metrics gathered from PostgreSQL system views, such as pgstat statements or pgstat activity. Having eBPF-based metrics allows us to see that our application generates 600 queries per second to our database. The latency is like super low. Our queries performed like in less than millisecond. Like average latency is less than millisecond. Like the majority of requests under 5 milliseconds. So here we have a heat map showing us latency distribution for our queries. With eBPF traces, we can understand the particular queries. So metrics are some sort of aggregations for individual events. For example, an application performed a query. We just incremented the metric and few metrics, in fact. But with traces, we are able to see individual requests. For example, it's pretty useful to analyze some latency anomalies. We just can select an area and see queries that perform slower than we expected. So let's start from the replica failure. So in Kubernetes and using Chaos Mesh, it's pretty it's pretty easy to isolate some pod at the network level because if we just delete the pod, it's pretty easy to detect for the control plane. But if we just make it unavailable through the network, it can be tricky to detect because it involves many mechanisms, such as you should have write timeouts, you should have some write readiness probes, and so on. So here is a specification for my chaos mesh. It finds and isolates a random replica. So let's see what happened. Here is an application point of view. In application, we have some performance degradation. We can see the errors. Application performed with errors because of database issues. So this happened during 45 seconds. So, and let's see what we can see from the application. And we can see that we detected that we cannot connect to the fenced replica. So network metrics show us that there were failed TCP connection attempts. In the application logs, we can see the related error messages. So we had connection timeout while attempting to connect to our replica. From Kubernetes point of view, like how we see that using kubectl or something like that, we can see that this affected replica, like readiness probes were failed. So Kubernetes, it took 45 seconds for Kubernetes to detect replica unavailability, and then it just deleted it from service endpoints. So our application, like when the application resolved like our endpoint, like PostgreSQL cluster replicas, the IP address of the affected instance like was like deleted from this list. So, and from the PostgreSQL perspective, we like since the instance was unavailable, we could not scrape PostgreSQL metrics and mark the instance as down. So we highlighted the problem, and we can see that like took some time to detect that, and then after like rebalancing, uh, the remaining replica received more queries than before. That's it. So pretty simple, but we need to keep in mind that like detection of instance availability is not happened immediately. It takes some time, but it's tunable by readiness probe configuration. Now let's repeat the test, but just make our primary instance unavailable. So we just change a bit selector here, like instance role primary, and then chaos mesh will fence our primary instance. So at the application level, we can see errors because we cannot perform queries on the primary anymore. So it happened 45 seconds at the previous scenario. And here is interesting detail that Cloud Native PG operator itself detected instance availability earlier than readiness probe, just because it uses Kubernetes control plane for leader election. So it works like it connects to the control plane, and the check interval is lower than readiness probe. And in this case, it initiated a switchover before Kubernetes marked the unavailable instance failed. And switchover itself took 45 seconds, and we in like on PostgreSQL dashboard we can see, oh, where is my marks? We can see that new instance now is primary. So switchover initiated here, and then like after a while we started to receive queries on new primary. So like pretty simple, and like this like when we see these switchovers like in real life, we can be more confident about our operator and high availability of our database. So like takeaways and findings from these experiments. Don't expect from Kubernetes to immediately detect failures. Depending on the readiness probe configuration, it usually takes some time. But it's not a bad thing, because if we will detect even like small, like short unavailabilities, it can lead to like unwanted behavior, because we will perform switchover be like without the reason. Once Kubernetes detects instance availability, it removes the instance from load balancing from service endpoints. Cloud native perfectly detected the need to initiate a switchover, and like after such experiments, we can be sure that if something happens even with primary instance, the operator will handle it. Uh, House engineering, from my perspective, is a great way to boost your confidence. And also, I personally use it for education because when I don't understand how some distributed systems handle failures, I can like deploy it into my test environment and perform such tests. And it's not uh, super like having right tools such as Chaos Mesh and Coroot for observability. It's pretty easy to implement such scenarios, and it took like a few hours to perform such real life failure tests. And when we deal with distributed systems, it's pretty, uh, I would say, crucial to make our system observable. Because if we deal with hundreds or in some cases thousands of services, we have to understand how they communicate with each other. We have to automate common pitfalls detection, such as network unavailability, node unavailability, and so on. And having right observability is the key here. And I encourage you to give Coroot a try. It's open source. It's distributed under Apache 2.0 license, so it's pretty permissive. It's based on eBPF, so and like it really can be integrated in minutes, even into big systems. It doesn't require any configuration, but if you want to increase digitalization, for example, it also support open telemetry, so you can it supports all um, metrics, logs, traces, and it also provides you with eBPF-based profiling out of the box. So just give it a try, and also out of the box, it provides you with advanced database monitoring, like it supports PostgreSQL, MySQL, Apache, Kafka, and so on. You will see everything. And we have two versions. One of them is community edition, which is open source and free forever. And enterprise with some advanced features such as SSO, single sign-on, role-based access control, and also we automated root cause analysis when you just can select some latency spike and Coroot will find the reason. So that's it. Thank you for your attention. If you have any questions, I'm happy to answer.